دكتور.
Yes. تفضل. Yes, sir.
Assalamu alaikum. Can you hear me? Can you hear me, Doctor? Professor?
Yes, I can hear you very well. Yes.
Okay, good. First, hello, good evening, everyone. I would like to welcome you all to the second day of our series, Renewable Energy and Power System, which continues for 7 days. My name is Ziad Nasser, and I'm the chairman of IEEE at University of High Branch. Our webinar today is about the challenges and opportunities for renewable energy integration into electric grid network. It's my pleasure to introduce my guest and our speaker today, the Professor Mounir Bouzguenda. Professor Mounir received the baccalaureate from Penn State University, and then he received the master and PhD from Virginia Polytechnic Institute State University. His master thesis title was A Study of Combined Cycle Power Plants Generation Expansion Alternatives, and the PhD thesis title was A Methodology to Study the Interaction of Renewable Energy System Dynamics with Fluctuating Loads. He took many positions at Sahar University and Sultan Qaboos University and a lot of positions. And now he's the chair of quality and coordination unit at King Faisal University. So hello, Professor Mounir.
أهلا وسهلا.
You can
شكرا
share our
جزيلا.
screen.
Yes,
يا هلا وسهلا فيك دكتور.
أهلا وسهلا. شكرا جزيلا. Thank you very much for your welcome statement, and I'm pleased to be here to talk about my research experience, and the focus will be on the challenges and opportunities for integrating renewable energy into the electric grid. And by renewable energy, I mean I'm focusing on the solar energy because of its relevance to many countries, including Saudi Arabia and other countries as well. And now I would like to see if you can see my screen, correct? You can see the presentation, correct?
Not yet, Doctor.
Okay.
Yes. Now it's working.
How about now? You see it, correct?
Yes, right.
Okay. Thank you very much. As Ustad Nasr has Ziad explained that my studies in the US involved basically the power system planning, operation, and the integration of renewable energy into the electric grid. So I will go ahead and go over some personal information which has already been introduced, but I'll just go through it quickly. Okay. It's not moving. I don't know why. Okay. Let me try again. Okay. Okay. Yeah, I can see it now. This information has already been introduced by the chairman of the IEEE branch in Higher University. Okay. Regarding teaching, yes, indeed, I have taught in several countries, including US, Tunisia, Oman, and Saudi Arabia at the current time. I also had some industrial experience in the US as well as in Tunisia, in the areas of renewable and reliability or analysis of electronic devices. My research experience, as you can see, basically focused a lot on the electric power grid and the integration of renewable energy. Some of the projects that I worked on: enterprise transition to smart grid in Oman, the development of new technologies involved in microinverter for solar PV application, the design of the eco-house power system at Sultan Qaboos University, and other studies included performance analysis, load flow analysis, quality assessment, and harmonic distortion analysis for grid or for distribution networks in Oman. I also had some work on water desalination using solar energy. This was done for 2 years in Tunisia, where we developed a prototype to produce, to desalinate or to um, make, well water potable. And it involves the instrumentation, the control, and other things involved. Okay, a little bit more information about the renewable energy energies, technical impact of distributed generation and on the distribution network. This is actually involves the load flow analysis for local grids or for at the distribution level, to be more specific. I also studied the economical and technical feasibility of the solar PV system for both industrial and residential applications. Okay, and also did an extensive study that proved that proper siting of solar PV installation on the grid will reduce technical losses and improve system quality. And also in terms of power electronics, involves the DC-AC conversion, including maximum power tracking and microinverters. By the way, microinverters refers to the DC-AC inverters that are integrated with the solar panel, and they do not require a transformer to upgrade or to step up the voltage. We all know that solar panels can operate at a voltage ranging from 12 volts to about 96 volts, a little bit more now because of new technologies. So the microinverter will come attached to the solar panel, and you can plug it anywhere in your house. So you might have a solar panel today in this place. Tomorrow you can take the whole thing and plug it to another place. So it has its own regulation, also DC-AC conversion and step up voltage. So it's ready to go with the right frequency and the right voltage level. Okay. I also did a lot of work on the effect of smart grid technologies on the capacity and energy savings as part of the transition project in Oman. Also, I worked on the remote measurement of solar PV and distribution transformer. A slide or a small introduction or a brief introduction about the microinverter. Okay, this is actually transformerless inverter. It does not need a transformer, integrated with the solar modules. The conception of this micro inverter without transformer is characterized by high efficiency, low leakage current, and zero crossing distortion. And the last item, this zero crossing distortion, actually helps a lot in reducing the power quality issues associated with power electronic devices, including the DC-AC inverters. The other major study, which I think part of the scope of this presentation, is the capacity and energy savings used within the concept of smart grid, where load sharing or load clipping has been utilized to reduce committing expensive generation units, also to reduce the technical losses in transmission distribution lines, also to reduce the dependence on fossil fuels such as oil and gas, these major fuels in the Gulf area. It also using solar PV using renewable energy is capable of deferring additional capacity, okay, to meet future power demands. And as a matter of fact, not just it differs, but also it provides customized additional capacity because of the small because of the modular size of the solar PV system. In other words, if you try to build a power plant using gas or oil, you think of using, let's say, 200 megawatt or maybe 500 megawatt plants. and that takes 2-3 years to build. Also, it will be built before the load demand has increased to that level. So the solar PV, modular installment, modular, construction, you can build 50 megawatt every year or maybe 100 megawatt. So by the end of 2-3 years, you reach the demand increase that you projected or you predicted in the long-term studies. So this is another benefit of using solar energy because it defers actually the additional capacity not being used. So basically, you defer the additional capacity that will save you money, maintenance, and engineering work, all these kind of things. And another thing, another benefit for the study is to promote using solar energy or as a renewable source. Just a small thing, a brief introduction on the load shape management. Okay, it is called actually load management. That depends on changing the load shape. You can probably use one of these four methods. Either you reduce the peak load totally by doing some load management, or you can move the peak load to the valley loads. Okay, so this is like deferring some energy consumption, some appliances to work at low demand periods, maybe early morning or maybe late afternoon. So this actually will increase the load factor of the entire grid, of the entire network. Or you can do just filling, where you can use some storage devices. So again, you try to minimize the difference between the minimum load and the peak load, and therefore, improving the load factor. And then we have flexible load shape. Okay, so basically you're talking about scheduling loads so that you can change the behavior of the load. This is not advisable because it's like random, but these ones here are very, are practically used in the industries right away these days. Okay. Now I will speak now about the benefits. I'm talking about the economical benefits of the load management studies carried for almost 4 gigawatt utility. Okay, we assumed 3 cases: 5% reduction in the peak load, 10% reduction, and 15% reduction. Now, this happened. Okay, actually, this is a load reduction not because of the load, but because we added solar energy. So we added solar PV systems, and you can see from the graph that there is a good match between the peak load of the utility and also the output coming from the grid, from the solar PV. Sorry, it's almost like this. This is actually a feature that helped a lot in promoting, or actually you benefiting a lot from solar energy. Now, in some other countries, some other places, the peak load could be a little bit late, maybe 6 p.m., 5 p.m., as in the case of many Western countries. So this happened to be a good match between the peak load and the maximum power generation coming from the solar panels. So for this, we assumed 4 cases. We base case is the reference. Then here we have 5% peak load reduction for 4 hours. Okay. Then 10% and then 15%. You can see with the 15%, let's call it penetration or peak load clipping, you can see that the load now almost flattened. As a matter of fact, it reaches a point where we have a new peak load early morning, like at night, midnight or so, or late evening. Okay, so this is actually the best scenario where you have almost flat load. Again, when we say peak load clipping, that means we are talking about using renewable energy at the premise, at home, at the factory. Okay, so this is the main feature of this. Okay, this table here, again, I should mention that the peak load or the size of this utility is about 4,000 megawatt. Sorry, so we're talking about 4,000 megawatt peak load. Okay, with the load profile you have seen earlier. So these are savings. These are savings. This is a plus. All of it. This is plus. So for 5%, the generation saving is about 1.2 billion dollar savings in generation, and for the 15% is about 2.3 billion dollars. Okay, you should know that, of course, I'm sure you know this, that increasing the peak load clipping by double, it doesn't mean that you double the savings. Okay, so here you have 5%, 1.25, 10% is 2.2. There is a gain of almost 1 billion. But then when you go to the 15%, you don't get 3 billion. You just get 2.3, like $132 million saving extra. Okay, so it looks like, when I'm sure now you can see this, there is a point where you don't gain a lot out of peak shaving, more peak clipping. Okay, for the transmission capacity, this is avoided capacity. Okay, because you're installing the solar PV system next to the load at homes, in the factory, in the university, even in commercial buildings and the streets. So you don't need a transmission. Here you have a saving of 226 million, almost 370, almost 400. Again, these are not linear, okay, because there's a point where you don't gain much more. Okay, so then we have energy losses due to the overloading of the transmission lines. Also, these are actually due to transformers, due to the transformers and transmission lines as well. Okay. Then we have a good saving from the emission and pollution, with about 300 million. Okay, and then 500, then 584 million dollars just pollution alone. You know that electric companies now must pay for the emission and pollution associated with power generation. So the total savings from the 5% is about 2.3 billion dollars, not billion, 0.3. For 10% is about 4 billion, and then for the 15%, 4.25. Okay, these are benefits. Now, in terms of upgrading the smart grid, meaning the cost associated with installing solar panels, installing smart meters, telecommunication, storage devices, to be able to support the smart grid transition. The cost, according to EPRI, Electric Power Research Institute in US, EPRI, estimated that, well, actually, I don't have the number for the US, but from that number, we interpolated that the cost of upgrading to smart grid for the 4,000 megawatt will be around 1.4 to 2, 1.4 billion to $2 billion to do this is the cost over the planning term, which is basically 20 to 25 years. Okay. By the way, this is I should mention this, very important, that this study was done for a 25-year planning period. Okay, so this is where we get all the saving. Basically, this 25 years study plan for that 4,000 megawatt, knowing that the peak load, I think, started from 4,000, ended up about 7,800 megawatt at the end of the 25-year period. 6% load increase on an annual basis. Okay, so this number, this is an estimate. Okay, and the prices now are going down. Okay, for the smart meters, for the solar panels, for the inverters, all this structure as well, maintenance, all of these are included here. So even if you spend $2 billion, okay, for the worst case, the 15%, okay, then you are gaining 4.2 billion. So that's a net gain of $2.2 billion for the utility over the 25-year period. Okay. So this is a long-term planning. Okay. Long-term planning for 25 years. The next study, well, this is, let me talk about the conclusion here. So it is a little bit hard to give a good price tag for the upgrade. Okay. Again, as I mentioned, April, the Electric Power Research Institute in the US estimated that it will cost the US grid, 50 states, it will cost 129 billion. No, this is actually the number of houses, 130 million houses almost, and it will cost 338 billion to about 476 billion over the 25-year period. Okay. So since there exists no such estimation, correct estimation or accurate estimation, our studies and assuming this peak load clipping for about 55 or 500,000 houses, it will cost anywhere between 1.4 to $2 billion. So if you take this number and you divide by the number of houses, this is like 500,000. This is like most basic about $600 or $6,000 per house for upgrade. You just divide this number by the number of houses. And I think now the prices are there because solar panels prices have dropped, inverters have dropped as well. Smart meters also are dropping in terms of prices, also improving in terms of efficiency and sizing and monitoring. Okay. So the previous study here is done on the long-term planning, like 25-year period. And then we conducted another study. Okay, this is actually to investigate the impact, the short-term impact of renewable energy. Again, with the focus on the solar energy, solar PV. Okay, so the goal is to find the economic and operational impact when large PV systems are incorporated into the grid. Incorporated meaning grid-connected solar PV. Okay. I'm giving a conclusion before I get into the details. The studies showed that the hydro availability, okay, whether you have water or not, generation mix. In other words, whether you have nuclear, coal, or just coal and gas and oil. So generation mix would be all types of generation, nuclear, such as nuclear, coal, oil, gas, etc. As well as the PV power output dynamics variation. Okay, this is also important as a function of the time of the year. The energy cost for the particular utility or for the particular network will affect the economic and operational impact of large-scale PV integration. Now, you will see the details for this conclusion here later on in examples. Results show that while hydro dispatch increases acceptable penetration level, okay, yes, hydro has a good impact on integrating, but the cost of generation and the generation mix will influence the break-even capital cost of the solar PV. And the study, it is estimated, or the study concluded that the break-even capital cost is around $968 per kilowatt to about $100 per kilowatt. The break-even here meaning if you integrate solar PV into the grid, of course you'll be saving money in terms of capacity, in terms of losses, in terms of energy. what will be the right price that you end up not losing, or actually not losing and not gaining. Or, in other words, if the price of the solar PV drops below $968 per kilowatt, then there are savings. Okay. So I think now these days, of course, these days the prices are almost there. The cost per kilowatt, this will include inverter, will include solar panels, structure, everything related to solar PV. Okay. Right now, this 968 is around 3,000, maybe 400 Saudi riyal, and here we are talking about almost 4,500 riyals per kilowatt. And the prices now are there. And by the way, this study is done in the US, okay, where the weather conditions um, are not as good as in Saudi Arabia, or the other way around. The solar PV performance in the places where we conducted the study has less energy. Well, actually, resources are the same, but the weather conditions made it a little bit uh, not as not performing as well as in Saudi Arabia. Just to give you an example, in the US, the number, well, on the average, 1 kilowatt of PV will produce around 3 kilowatt hour per day. However, in KSA, the same 1 kilowatt will produce anywhere between 5 kilowatt hour to 6 kilowatt hour per day, depending on where you are in the kingdom. So what I'm trying to say here is the break-even cost for Saudi Arabia will be much less than this. Okay. So now we go into the details. Okay. To get a better understanding of the impact of the generation mix and the performance of the solar PV, I did some performance analysis for 3 solar PV stations, okay, known as one is Vista, Vista, Raleigh. These are actually 3 different locations, okay, and they're about maybe 300 to 400 kilometers far away from each. So the weather conditions are not the same. I mean, well, so they don't get affected with the sunrise or the cloud or the rain or the temperature at the same time. So what we did, we looked at the maximum ramping rate, meaning the variation of the solar PV output on the for each hour. Okay. Hourly ramping, meaning how much the PV output will change on an hourly basis. So we looked at we had actually long-term performance of the solar PV stations, these 3. The For the first station, for the first system, the ramping was around 0.23%. Okay. For the next station, about 0.5, and for the third city or the third place is 0.71%. Okay, now if I'm using one station at a time for this, these are actually the numbers. But if I merge all 3 of them and I use what we call the distributed aggregated output from these 3 systems, then the variation will be, of course, would be like an average value for this. Okay. This is actually increasing, decreasing, minus 0.5, minus 0.6, minus 0.69. On the average is minus 0.42. This is for the month of January, typical day in winter. Okay. And then in April, you can see the variation are a little bit different, especially coming down. Then in July is a typical summer day. Okay. Actually, we looked at the maximum power for those days. You can see here January is the peak load is high, about 8,134 megawatt. This is because of heating. And then in the summer, because of the air conditioning. Okay. And then April, spring, and fall, these are mild seasons. So their peak load is less than than the winter or the summer seasons. Okay. So the point out of this, that if I'm looking at the variation of the solar PV per station or per system, per location, I get, you know, what do you call it? More or less variation than the distributed. Okay, and this is actually observed throughout the year. If I look at the load, distributed generation is variation is more than the load. You can see that in all cases. So this actually will cause a problem. Now, this variation might not happen at the same time, or the ramping, up and down might not happen at the same time, but it gives you that a variation of 21% in the load, okay, could only accept what is equivalent of this. So if you have, let's take this number here, this 9,000 here, let's say almost 10,000. So 0.16 of 10,000, that will be divided by 100. Actually, it's about maybe 150 megawatt. If the PV is 1,000 megawatt, this would be 320 megawatt. Okay. So it means that delta load is greater than is less than delta PV. So the variation in the load, okay, of course, for large system, okay, for large PV systems, you'll see this effect later on. So again, that's why we have the study called the performance of variable PV under fluctuating loads. Okay, so somehow the generation or the rest of the generation must accommodate for the change in the load and the change in the PV output. Okay, this is one observation. The other observation that this is an hourly basis doesn't give us a good idea. Okay, because it's like an average value over the hour. Then what we did, well, actually, this is in terms of load. So you can see here, 1,000 megawatt for the load variation. This is a significant impact. A drop of 415. However, the distributed generation is 250. So this can be absorbed. However, if you take one system at a time, here you have 149, which is much less than the load. Here you have more, or actually almost the same. Okay, so there you might have a problem here and here. But you can see the distributed, the aggregated one, will correspond better to than the if it is just by itself. Okay, and I think the worst case would be for this location here, 428, 187, 257, 233. Okay. Now this is 10 minutes. This is actually more important than the hourly values. Okay, more important meaning in terms of significance. So for the minute performance, we have for the first location is 2.3%. Okay, variation. The load is 0.3%. This is like 6 times bigger than this, 6 times larger than this. Here we have about twice. Here we have about 20 times more than the. Okay, so the variation. Of course, by the way, if we look at the summer, we should have better values. Okay, no, not even that. Here, 0.696%. The load is more stable than the PV. Again, in this situation here, I know the place very well. The weather changes almost every 5 minutes. Okay, So you might have clear skies in the morning, and then it starts raining, and some clouds and wind and things like that. Okay, but you can see that the PV intermittency variation is very significant. So it's going to be very hard for the load or for the grid to absorb all of this variation. But nevertheless, if you have a distributed system, you have less numbers. Here you have 2.2% versus 6. Here you have 2 versus 5, 5, 5. Here you have 2 versus 4, 5, 6. Okay, it's much better. So now, one thing is, if you look at the performance for 10 minutes, you see more significant changes than the hourly values. So we don't rely on the 1 hour, we rely on the 10 minutes. So when we did the economic dispatch, we did it on the short term, every 10 minutes, not every 1 hour, because the 1 hour will not give you the accurate, will not give you accurate results. 10 minutes, 5 minutes will be better, but we do not have the measurement for at that point for 10 minutes. We can have only for we have only for 10 and 1 hour. Okay. We don't have for a shorter term. Okay. Now for the study, okay. Actually, this is an extensive study. You'll see how many cases, the number of cases we dealt with, but we assumed all types of generation. We had nuclear, coal, large oil units, small oil units, large oil units, gas units. We have pump storage in the scenario as well. We have hydro. Okay, sorry, and then we have the interconnection with the neighboring utilities, with the neighboring networks. We allow 500 megawatt for interchange. Either way, you export or you import. This is actually good for exporting extra PV in case you have more PV which you cannot absorb into the grid, into the network, so you just transfer to neighboring networks. For pump storage, we only accept 500 megawatt, and for hydro, maximum is 1200. It exists, as a matter of fact. Such a hydro availability of 1200 megawatt is exist in the system. This is the study scenario. We have long-term planning, then we have weekly planning, then we have the 24-hour unit commitment, then we talk about the short-term analysis, economic dispatch every 10 minutes. Okay, so long-term, of course, to be able to know how many units do you need in the next 10, maybe 25 years, and then weekly scheduling. This is actually to allow to prepare yourself for when to pump the water into the reservoirs. You cannot do this over the day. You have to do it in a long period. So basically, you schedule when you pump and when you, of course, discharge from the dams, so that from the reservoir, so you produce electricity. And then this 24-hour unit commitment. This is to prepare the fast ramping units, such as small oil and gas. Okay. Long-term planning is also good for nuclear, for large power plants such as nuclear and coal. And here you have this the automatic generation control, load frequency control, to adjust the generation level of the units. Okay, we do not deal with this. Okay, we were not involved in this. Okay, this is a much smaller time interval. We dealt with economic dispatch to a 24-hour unit commitment, and these two. So this is only the scope of the study here. And by the way, I should mention that this project was actually sponsored by EPRI. Okay, we conducted this research for EPRI for a 2-year period. EP, okay, here. I cross it down and write it down again. EPRI, Electric Power Research Institute in the US. So I keep doing the same thing. Okay, EPRI. supported and funded the project for 2 years. Okay, now these are the scenarios we undertook in the study, 18 scenarios. Okay, and what we did is I conduct the economic dispatch for 1 day. Okay, using generation mix A. Okay, have A, B, C. We have 3 scenarios. Okay, which is has to do with low hydro, low transmission system intertie. Okay, and okay, you can see them here. Hydro here. Okay, so basically for each, so here I'm assuming actually I got another location here. This is actually where Fista is. Okay, this is the first station, number 1, number 2. So what it is, just to give you an idea, this assumed that my power plant, which could be maybe 500 megawatt or 1000 megawatt, is located in Richmond with the prevailing weather condition that affected the Vista performance. So basically, this is like the PV system, the 500 or the 1000 megawatt is located in one place. Then we did the same economic dispatch using another location for the solar PV system. Okay. Here we have hydro availability, meaning even though I have 1200 megawatt, okay, of hydro, I'm only using 20% of it, so which is about 240 megawatt or 250 megawatt, something like this. Okay. Intertie or interconnection with the other networks, 500 megawatt. Then here I allow to use pumped storage in cases 13 through 18, no hydro here. Okay. And of course, we talked about the cost, high cost, fuel cost, and things low cost, high cost, many other scenarios. Okay. This one here, this is to give us an idea of the system operation for a medium weekday in January. Okay, where you can see here the different weather conditions. This is a rainy day, assuming that, of course, cloudy day, and a clear day, partly sunny and cloudy. And this is a variable cloud. This is intermittent. So here you have no sunshine at all, so it's raining all day, which happens to be many days like this. I'll show you some numbers. Maybe 2 or 3 days a month you have rain. So basically, output of the solar panels is almost zero. Sunny day meaning it's clear all day, partly sunny with some clouds. This is more sunny than cloud. Here is more cloud than sunny. And this last case here is intermittent. So a lot of variation in the weather condition. So when it was rainy condition, we cannot get any PV included in the grid. It does not accept. Of course, it's zero. It's not there anymore. Now, when it's sunny, you can get about 3,200 megawatt. So this 3,200 megawatt is accepted on all these 3 cases. But for intermittent, it dropped to 2,200 megawatt. So here, of course, this is a long, big software, comprehensive software that takes a lot of parameters into account, okay, including ramping, optimization, iteration, all this kind of thing. So for this, it accepted only 2,200 megawatt. Just to give you an idea, this top one is when you have, this is low. I think I reversed this. Well, actually, I didn't. Sorry. This is low hydro, meaning the 20% hydro. When you assume no hydro is available, okay, this is again hypothetical case. The acceptance of the PV dropped from 3,200 megawatt to 3,200 megawatt to 2,000 megawatt. That's a loss of 1,1200 megawatt. Same thing here, almost same. And then for the crowd, it accepted only 1,700. So from this figure here, okay, you can see that the availability of hydro, okay, or actually the absence of hydro, will reduce the acceptance of the solar PV. And if you compare this to this, okay, if you compare this number here, for example, for a sunny day, you go from 3,000 to 2,000, that's a loss of 1,200 megawatts. So hydro is very important. But nevertheless, 2,000 megawatt is a good number. Okay. And then here you have the other parameters such as hydro generation, nil, PV generation, of course. Here this is per day, 24 hour. Production cost, we're talking about $2.6 million per day. With low hydro, we're talking about 3,000 or $3 million per day. Okay. This actually, this study here, I wanted to emphasize on the distribution case. This scenario here, I'm assuming one location for the solar PV, only one location. Like say, for example, if we're installing this in Al-Hasa, we will have a big, solar power plant next to Al-Hasa over maybe 2 kilometers, square kilometers area. Okay, that we call it central. Okay, distributed is like having, let's say, 500 megawatt next to KFU, 500 megawatt next to, for example, out there in the, for example, Al-Uyun or Baqiq, something like this. That's what. So basically, you split the 2,000 megawatt into 4 different places. That's what it means by distributed. Okay. Now I'm sure for KSA, the weather conditions are pretty much the same. Yeah. So basically, it will not make a big difference. As a matter of fact, if you have it in one location, but if you have one system in an eastern area, for example, we're talking about a national level, one on the east coast and one on the west coast, one on the north, one on the south, definitely that will make a difference. If it is not a difference of time, if it is not a difference of weather, okay, it will be a difference of time. We know that the sun set in an eastern area, okay, and for example, Khubar is about 45 minutes ahead of that in Mecca or Jeddah, okay, or Medina. So that 45 minutes actually will help. Of course, we're talking about national grid that is interconnected. So definitely having the solar PV distributed over Saudi Arabia, if you will gain from both the local or the time distribution, time difference, and the weather. I'm sure that the weather conditions in the eastern part are quite different from the one in the center and from the one in the west, mainly due to the closeness to the sea, humidity, lower temperature, dry weathers. All of that will affect the performance of the solar PV. So this actually we can increase the system here. So I'm looking at the maximum PV system accepted. Okay, I'm going to change the size of this. This is the PV size accepted. Okay, without any issue, without any. I mean, that's what the system will accept. So if you have it in one place, in this case, for example, Richmond, the maximum level is 2,000 megawatt, 2,600 megawatt in VSTF, and 3,200 in Raleigh. And for distributed system, the maximum level is 5,000 megawatt. So you can see that having the solar PV system, or actually entire system distributed over 3, 4, 5 areas, will improve the acceptance of the solar PV. It will increase the penetration level of the system. Now, this is one thing. Then the other impact will be on the economics, from the point of view economics, also the spinning reserves. So you can see here starting cost. For example, here is 11,000. This startup cost is due to the fact that sometimes you have to turn off small units, such as a 50 megawatt gas-fired unit or oil-based unit. Then you turn it on. So basically, turn on and turn off will cost you some money, maybe $200 per startup. Here you have 11,000, okay, because the intermittency is high here. But for, of course, this is not the same level. Here you have 5,000 megawatt. Here you have 8,000 megawatt. And here you have 2,600 megawatt, and the cost is 11,000. So there is a really big impact on the startup cost. Okay, even for 2,000, you still have 5,000 megawatt. Okay. By the way, you know by now that PV, because it's intermittent, okay, it will allow, or it will actually cause some small units to turn on and off as needed. Okay, that's why you see here. You can show it again. For example, here for 1,000 megawatt, you have $7,300 for startup. More PV, more startup, more cost, higher cost. Okay. Now looking at the this one here, system lambda. This is actually, if you are taking a power system course or power system course for economic power system planning and costing, this system lambda meaning that all the units would be operating at the same incremental cost. Okay, so here the incremental cost is 95 mils per kilowatt hour, and here you have 87. So this drop of almost 8 mils per kilowatt hour. What it means that okay, this is actually in terms of the software, the tools, and from the point of view practical, is that the system here is working, is producing electricity at a lower cost. That's what it means. So if you look at this table here, this is the worst case. Here we have 95.42. That is the highest. Of course, we have no PV. Okay. So as the PV goes up, it will actually drop the incremental cost to about 87. This is actually the lowest, and then there is another one higher lowest. Okay. And here you see the energy savings. Okay. So actually, this one here, for installing 5,000 megawatt of PV, energy production saving is $1.5 million per day. 1.5 million per day. 1.5 million per day. So if you multiply that by 360, okay, 365 days, then that's how much money you save out of this 5,000. Then you divide by 5,000, you get your saving per kilowatt. But the story, it is not this way. Why? Because here, this day here could be the best PV system. Okay, the best performance. How I can say this? Let's say assume this is for a sunny day. Okay, so what do you have to do? You really have to do more studies, more economic dispatch for typical days, and then you take the average. You divide the year into a number of days with rainy weather condition, okay, with partly cloudy, with sunny, and this. Then you take the average. That will give you the good estimate, which is actually the scope, which I will discuss later on. Okay. This picture here shows the load profile. Okay, a typical day. Can't see the date here. I think I have it. No, maybe. No, I don't have it. I can't remember the date to be on here. Whether some, well, you can see there is a variation on the output of the solar panels, of the solar PV system. This is the load, you can see it. 500, this is the load on the right side. 7,000 megawatt is the minimum load, and about 11,000 megawatt for the peak load. And for the PV system, I'm using almost 1,700 megawatt. And here you see the PV performance of the same day, by the way, okay, of the same day for each system. You can see this one is very variable. This small one here is less variable. But if I distribute them, if I use the aggregate, I'll have a better, you can see it here, I can just follow it with the red. This one here, you can almost see, there is actually some drops, okay, but nevertheless, it looks like smooth, okay. It is smoother than this and this. That's why you get a better ramping rates or small ramping rates for the PV system. This figure here actually highlights the peak load coincidence, or the what we call the peak and low, the peak load and PV match. Okay. In the winter, peak load is early in the morning. Oops, sorry. Oops. Why it doesn't work? Sometimes it does, sometimes not. Okay. This is a peak load, and this is PV. It's like a shift almost 2 hours. In the spring, yes, they have a long actually peak load here. It's maybe 8 hours, okay, or more. This is a good match. You can see here the peak load. This is a PV at the same window, time window. And the summer, okay, the peak load is after the PV output, maximum output. Okay. And here you can see there's a peak load here, there's a peak load here, and the PV is in between. So there's a good match here. This is very good. This will help actually getting more PV useful to drop the cost, because at the peak load, you're running the most expensive units. Here you still are in the area of the peak load, so this is good, very good too. And this one is, but of course, you can always use the renewable energy because it's there, it's available, so you better use it. But it's not going to give you more economic values. It's going to give you less economic value than this case and this case. Okay. This is another case with intermittent, okay, generation. This actually justifies the same scenario, okay. But this one here, this is like a okay day, but more actually better performance. Here you have some intermittency. This actually validates the hypothesis that there's a peak load match here, but here there's no matching between the peak load and the PV output. Okay, now here, yeah, this one here, yeah, this is very important. Remember, we were talking about the annual cost. Okay, so the number of days of the weather conditions in this area in January. Okay, we have rainy days, sunny. Okay, so this one, I don't know, I did not include the numbers, but let's say this is 5, this is 7, this is 3, this is 8, and this is, let's say, 10. So you add them up, you have 31 days for January. So what you have to do is look at the savings, okay, and you multiply it with this number for each one here. You add them up, you come up with an average value. And then January, February, and March are the same. Then May, April, and June are in one group because these are seasons. July, August, and June, maybe August will be the same. Then you have October, November, and December to be the same. Okay. So you average out all these numbers. So you look at these numbers here, the savings here. You multiply them with the number of days per this, and then you multiply it by 3 because you have 3 months per season. You do the same thing. And then we were able to do this for many other cases. And we end up having this scenario to be able to see whether it makes a difference to have a small PV system or large PV system. Okay, here it's not very clear, but I can show you here on the bottom, on the horizontal scale, we have the PV size. So here we have 25 megawatt, 50 up to almost 5,000 megawatt. Okay, and these numbers here, this tells you, okay, if the price per kilowatt, dollar per kilowatt. Okay, this one here. If you integrate 25 megawatt and the price of the solar PV is $1,000 per kilowatt, it is absorbed. And it's good. You benefit from this. And this price would be valid, okay, for almost stays for a quiet period. You can see here, this number is here, almost, but not really, but there is a difference of maybe $50, so anywhere between $950 to $1,000 per kilowatt. It means that if I install one PV system of 3,500 megawatt at $950, I start to benefit. If the price goes below 950 or maybe 800, that I know, I'm sure I'm gaining. I'm benefiting from the system. So these prices, then, we talk about 10, 15 years ago, these prices were not there. Right now, nowadays, the solar PV costs less than $1,000 per kilowatt. Less than 1,000. So now, if the network allows me to integrate up to 2,000 megawatt or 5,000 megawatt, is going to be for sure, it will be fully acceptable from the point of view economics and from the point of view of operation. Okay. Now, if I'm optimistic, okay, and I say I want to install not 2,600 megawatt, no, I want to install 5,000 megawatt. For the electric company to be in a good position, then the price of the solar PV per kilowatt has to be like $150 per kilowatt. Okay, so there must be here an optimal value, okay, or a trade-off between the price per kilowatt and the acceptance. Okay, so if in 20 years or 15 years from now, the price of solar PV goes to $50 per kilowatt, okay, then it is possible to integrate up to 5,000 megawatt. So right now, if I'm looking at the years, I don't have the current values, okay. Somewhere here, okay, maybe 900, 1,000, okay. Of course, this curve, this graph here, is based on scenarios. I'll show you that scenario, what that scenario is. Okay, this is for case number 9. I have to go back to the case number 9. I have other cases. Case 1, which I missed, I think. Let me see here. No, I don't have case 9. Case 1. This is case 9. This is case 10. Case 10 requires higher solar PV cost. Actually, almost $1,200 per kilowatt. The previous case is 1,000. This case is 1,200. So this is more expensive. Okay. In other words, the other case, number 9, is here. So we're about 300,000 or $300 per kilowatt extra. So this case here has to wait, for the PV cost to go down, which actually now it's below that. So it's below 1,200. I think it's around $900 per kilowatt. So they are here. So I think they can accept. I don't see it here. This is 900. This is 800. We can accept up to how much? Okay, maybe 3,600 megawatt. Okay. This is case. Sorry. This is case. Okay. That's because I'm oversizing it. Okay. Sorry, I don't have the case. Case 18. I have it here. Case 18. Look at the prices. This is 600, 800. This is 900. This is the best case. This is the cheapest case, as a matter of fact. This is the lowest cost per kilowatt. I think we are there now. Okay, so up to how much? 3,800 megawatt. So 3,800 megawatt can be accepted without losing. But if the prices are higher than this, definitely the electric company has to pay the difference. Okay. I think this is another case where we have this case number 10. Yeah, this table actually we use to come up with the break-even capital cost. Okay. We also conducted some other studies, 6 more cases that showed us some with different, of course, generation mix, and we have new values. Break-even capital cost 1250 here. Sorry, this is actually the max you can have. Then it goes down to 1,000 when you have 1,700 megawatt. And to accept 5,000 megawatt, you're looking at a price of maybe $50 per kilowatt. So this is not beneficial at all. I mean, if you are here, this is not possible. The price didn't go that low to reach 750 or 500 megawatt. So we are looking at this area here, up to 1,700. So the matter to accept solar PV integration to the grid, you have to look at it from the point of view of how much the network can absorb in terms of power, in terms of ramping, in terms of spinning reserve, and also you have to look at from the point of view economics. Okay, for the electric company to gain from the solar PV, you have to look at, of course, we all know this, that the cost of the PV has to be, the lowest. Okay, but technically this is not possible. But if you look at the history of the prices evolution for the last 20, maybe 25 years, you can see that the prices are going down. Okay, and there will be one day where we are actually operating at maybe $500 per kilowatt, maybe even less, $300 per kilowatt. Therefore, we can absorb, the electric company or the network can absorb up to 5,000 megawatt without losing money. Okay, of course, all the savings will be, of course, there will be a lot of savings, pollution, reduction in losses. Of course, all this will follow. Okay, this is actually, let me reduce the size here. Okay. This slide is supposed to be earlier, but it just shows the effect of the ramping of the fuel. I mean, of the conventional power plants. Okay, actually, we did not. I didn't. I mean, this is like on the side, low ramp rates for the conventional generation, high ramping rate. You can see low ramping rate. What I mean by low ramping rate is the fact, for example, here, um, when you turn on the generator, the process of getting from the minimum power of the unit to the maximum power is going to take some time, maybe sometimes half an hour, maybe 1 hour. So the ramping rate will be the percentage of the capacity increase per minute. So some units can increase, let's say 5 megawatt per minute. Some of them would be faster, they'll be 10 megawatt per unit, per minute. And some are slow, it's going to be 1 megawatt per minute. Now, to get a full picture of this, let's say you have one combustion turbine running at let's say 50 megawatt. Okay. And then the PV output drops by, let's say, 10 megawatt. This is an example. Actually, this is the whole thing is what's all about, the economic dispatch. So the combustion turbine is generating 50 megawatt, and the PV was, let's say, was 100, and it drops to 90 megawatt. Okay, that's a drop of 10 megawatt. Now, the combustion turbine has to provide the drop in the PV, correct? The 10 megawatt. So the combustion turbine has to go to 60 megawatt. It's a question now, how much time does it take, okay, for the CT to go from 50 megawatt to 60 megawatt? If you can do it within the 1 minute or so, then the PV output drop can be compensated by the CT generation increase. If the CT is not fast enough, maybe it can go to 55 megawatt, but then the PV might go up to 95, may go up to 100 megawatt, because there was some cloud moving on. It just dropped the PV output by 10 megawatt, then it disappears, so the PV is given. So this is what it's all about, okay? Is the ramping rate of the conventional generation to absorb the PV variation. So for low ramping rate, meaning slow units, okay, it's going to take a lot of time to add some megawatt to its generation, because this takes time. We're talking about heavy equipment, and a lot of control, a lot of instrumentation has to be, a lot of consideration has to be taken into account to increase the city, and we all know this. It's not a small car that you turn on and you move on. No, it's going to take some time. So here we're assuming slow CTs, for example, slow combustion turbines, and here we're assuming we're using faster CTs. So this affected actually the penetration of the PV. Okay, here you have low for a weekday. I think this is a flow, flat load. Okay, weekday. Whether you have high ramp or low ramp, you still have the same number. On the weekend, this is actually, it happens to be a weekend day. With low ramping rate, you got 2,000. With high ramping rate, you got 4,000 megawatt. So that's an increase of 2,000. Okay. على فكرة, this is actually when we have a good weather conditions. Okay, sunny day. And here, another day, 3,200. Here we have 3,800. Now, if you have cloudy days, okay, then you're not going to have, but you're going to see some impact. For the low ramp, here is accepting 2,000, here is accepting only 900. But when you have high ramping, this is actually where you see the importance of the high ramp. You get 2,000 in either way. Okay, so this shows you that the ramping, meaning that having fast combustion turbines, having fast ramping generation, will improve the penetration or the integration of solar energy. Of course, there are other issues involved, such as the frequency, the interchange with the other companies, with other networks. But this shows actually importance of the ramping of the units on the on the on using on deploying the solar PV. And here we have a very good case for the cloudy day. Here we have 2,200 megawatt with fast or high ramping rates. We got 4,000. That's an increase of 1,800 megawatt. And here we have okay, increase of 3,400, 3,800. Okay, and this actually summarize that the increase in variable condition is 1,100. That's the best. That's the best. Okay, this is actually increased due to the increasing the ramping rates of the cities on the gas turbines, etc. So the study, now I think I come to the conclusion. The study also proved that the connection between the electric grid and the neighboring networks to accept or decline the transfer of the solar PV extra output, whether it's extra in terms of exporting it. If it is less, then it's important. The study proved that the ideal prices or the ideal cost for solar energy system is around $1,000 per kilowatt, or in countries with low and intermittent solar PV performance. And we're talking about countries that have like 3 hours per day or maybe 3.5 hours per day, such as US and Canada. The best price, the break-even cost should be around 1,000. For countries with high solar resources such as KSA and the neighboring countries, the break-even capital cost is higher. Actually, this is not bad thing. This is not a negative impact. It means in Saudi Arabia, even if you use solar PV with a capital cost of more than $1,000 per kilowatt, we are gaining. Okay, there is a benefit to the electric company, and of course that will translate into lower costs for electricity and also the extra money that the company can actually use some other projects, extend and do other things. So that's what it means here. Means that even if the capital cost is more than 1,000 kilowatt, the company still makes money. Okay, here it says good weather condition, high insolation levels. The solar power output is entirely dispatched, yielding higher energy values. And if we do the same study for countries such as KSA, we're going to find out the prices may be 700, maybe $800 per kilowatt. I come to the conclusion of this presentation, and I thank you very much for your attention. I know I have been talking for almost 1 hour and a few minutes, 1 hour 18 minutes, and now I give you the floor to see if you have any questions. Please let me know if you have any. Thank you very much.
Okay, thank you, Dr. Mounir. So I think we get to the question part. Please share your questions and comment window. So do you have any questions? So let's wait just for a minute to check if there is any question.
Please, yeah. Is this session recorded? I didn't ask if it's before.
Yes,
this is recorded. Yeah.
Yes.
It's recorded. Huh? Okay.
I think there is a question, Doctor.
Please, yes. Do you read it for me, because I don't see it.
Okay. What makes a weekday different to a working day?
Okay.
Why accept more PV generation in weekend day?
Weekend day, yeah, that's a good question.
I think the difference between weekday and weekend day.
Okay, weekday and weekend day is like Friday here. We know that on Fridays is a weekend, so we wake up a little bit late. We go to prayer and then okay. So it has to do with the fact that during the weekend companies are not open. For example, here in Hufuf, Mazra is not open until 12 o'clock. Uthayim market is not open maybe until 4, 12 o'clock. So in the weekend, a lot of stores are not open, schools are not open, factories are not open. Okay, so what happens is you will have different consumption. The electric consumption in the weekdays اللي هي عندنا Sunday through Thursday, you get all this, and the government also is working on the weekdays. On the weekend, is not working. So that makes a different load profile. I wish I had. I can show you this. So, but not right now. I'll tell you what the difference is. The load profile for the weekend will be flat, almost flat compared to the weekdays, because on the weekdays you got schools opening in the morning, and then around 2 p.m. schools would be closing, and then people go back to work. So you get a lot of output. You get a lot of dynamics in the on the electricity demand. So, but on the weekend it's going to be a little bit flat. So, and that load during the weekend is basically homes. Okay, maybe turn on air conditioning, turn on. So there is no sudden increase in the demand. So therefore, the PV is absorbed within that thing, within that within that. What should I say? It can be absorbed easily because you don't have that much increase in the demand that will force the PV system. Now you might have lower acceptance, okay, in some days, but usually on the weekend it should be accepted. By the way, uh, actually we were talking about the effect of the conventional generation on the PV. Actually, the PV can cause problems to the conventional generation. It's a two-way relationship. So the behavior of the load and the behavior of the PV will affect the combustion or the conventional generation. Okay. Now, in some cases, because we only did for typical days. Now, this might not be true for some days, for some weekends. Okay, but I know for a fact that the weekend load profile is flatter than the weekdays. Also, it has less fluctuating, less variation. If you look at the ramping rates that I was talking about, maybe for the weekend it's going to be almost zero. Okay, but for the weekdays, you have stores opening, you have factories, you have schools, you have experiments, you have a lot of things going on. And you might have some experiments, some loads that run for half an hour, then turned off. That doesn't exist in the weekend, unless when you have the stores opening at 4 p.m. That could be also increase in the load, but steady, steady. Okay, this is a good question. Thank you very much.
Okay, I think so. There is another question. So I have to end this seminar, but before ending the seminar, Doctor, we are pleasure to express our gratitude to you for your efforts and give you a certificate of application from the IEEE Club. And I will share my screen here. So thank you very much, Professor
Yes,
Mounir
okay.
Bouzguenda.
Okay, thank you very much. I
We
appreciate
your time, Doctor, and we hope to see you again in next seminars.
inshallah, I'll be there, and I appreciate your persistence, your hard work to make this event really successful. I know that Ahmed Azhari was actually involved in this. He consulted with me. He consulted with other faculty members in the department in the College of Engineering at King Faisal University. And I really recommend him for this great work and coordination. Thank you very much.
Thank you again, Dr. Munir, and thank you, Ahmed, and thank you for all branch who's work with us. And see you in the third day, inshallah. So
Thank you very
see you
much.
again.
Have a good night.
Thank,
See you.
thank,
Thank you very much.
thank you.
Good night.
Bye, bye. Thank you. Good night, Dr. Munir.
Good night. Bye.